Hello. Yep, now it's working. Okay. Good afternoon, everybody. Can you hear me now? Okay, glad that the Zoom has changed the mic setting automatically. So everybody can hear me right now. Oh, thank you. Perfect. All right. Thank you, Ayush. Thank you. Okay. So what we had covered last week, we did cover the parts of the network layer with the TCP layer. We will continue today still with the OSA layer as it is. With the last part of the last week lecture, I have mentioned that the two main functions and services for the layer number three, which is the network layer, one, logical IP addressing, which is like allocate or assigning IP either version 4 or version 6. The second service or function, that's routing. Okay, what do you mean by routing? How to send the data or how to actually determine the path which will the packet take it from A to B. We call that routing. So determination of the path of a packet, we call that routing. What type of routing we have? Well, we have two types of routing in general. One of them is the static routing. What do you mean by static routing? Okay, static routing is I want to specify a specific path direction, which is the packet will take it regardless of the other hubs, other routers. So if I want to send the data from A to B through one specific direction, we call that static routing. And that has cons and pros. We will cover that. The other option, which is the most used, the dynamic routing. Okay, can you give us a little bit hint about which one and which one, and when we use that, when we use that? Okay, usually we prefer to use static routing if I want to have a security that's secure. Secure means like take that static path. Don't go anywhere else. Don't pass by any other router. Those routers I want you to pass by. We do that in term when we need to provide a higher level of security. Another option or another reason, when we try to create a backup for the dynamic. So if the dynamic routing fail, I need to have something as a backup to work in terms of the failing of the dynamic routing. Okay, so that's the two main reasons. There are other reasons, but these are the main cons, which or the main reason we use static routing. One, security. Second, as a backup. Okay, so what is the other option for us to do routing? And by the way, that's not too many. Like if you have the percentage, less than half 5% of the world routing is not it's static. So most of the routing usually done by dynamic routing. So what is dynamic routing exactly? Dynamic routing, we leave that the choose the determination of the routing the packet will take to the router, to the router itself, the router itself. So how the router decided which path will take? Oh, the router come built in with what we call it algorithm. Really, yes, different algorithm, which we will cover soon. So the router will run some calculation and then decided that do I need to take serial 0 or serial 1 or serial 111, like that? Which one I'm going to take? That's what it is. So what exactly the if I want to compare between static and dynamic, very quick here. If I want to just make, we will go back to the each one. So if I want to compare between static routing and dynamic routing, which one provide what? You may see that with the static routing, I have one direction, one static destination. That's it. They go from A to B through that direction. With the dynamic is not. The dynamic, as I explained to you last week, it can take multi directions. How we configure the static routing? Usually manually by command. Watch something like that. The command usually, for example, let me just make sure that you get that clearly. This is PCA, PC1, PC2, PC3. This is 172.16.3.0. That's 2.0. That's 1.0. Then I have 192.1, 192.2. So what do we do exactly? I'm here, I want to configure that router. Assume that you have multi-routers here. Can the direction take off? So I want this one to configure it as take that direction. So if I'm linking to another router here, another router there, another router here, now take that direction. So assume that that router number one, has other interfaces, but I want that to take serial 00 from here. So what we do exactly, we configure something called the next hub. What is that? Here it is. Okay. So IP route, that's the commands usually we use. Can you route 172.16.1.0, 255, 255, 255 to the serial 0, 172.16.1.0. Okay. 192.168.1.0, which is this one. In short, if you want to reach that network, send your packet over here. What we call that the next hub. That's serial 00. So I'm here. If you want to reach 172.16.1.0, send your packet here. If you want to reach 192.168.1.0, send your packet here. If you want to reach 192.168.2.0, which is this one, the network, the whole network, send your packet to that interface, which is the next hub. We have the assumptions that this router usually, minimum, the router usually come with 2 slots. Each slot can carry, if I want to put, for example, the HT2, I can put 2 of them, 2 slots. So I can put four serial interfaces in one router. Sure, I can add more if I want to, but minimum of that. So we assumption of that, take that one and leave everything else. That's what we usually do. And that has to be done manually. Okay, what is the problem with that? I want to change that. Or something happened, I need to change that. So what we need to do, we need to go back, configure that again manually. Every time we need to have some changes, we have to do that manually. And that's one of the cons, which is the disadvantage of the static routing. So yes, it's nice, it's whatever, it's okay, it's secure, but at the same time, it has management overhead headache. Smaller routing, yes, because that's an advantage. Smaller routing means that you have one entry in the table, which I'm going to show you in a few seconds or a few minutes. But the other dynamic, you have multi options, multi-step, multi-routing, multi-entries inside the table. Okay, in static routing, you don't need algorithm. No algorithm, no protocols, nothing. You just put the command will take it. With the dynamic routing, I need to use two of the main approach, which we will discuss. So either something called distance vector or link states approach, both of them. And each one use different algorithm. That the static require less computation. Yes, computation means resources, CPU and RAMs. With the dynamic, yes, it consume extra resources. And you will understand why is that when I show you how the table works. This one is better security, less than security. This one, we use it usually in a smaller network. The dynamic one, we use it in a big, massive network. And that's the most used, the dynamic routing. So we have static, dynamic. Each one has cons and pros. Yes. The one we will focus on today, for example, the dynamic. What's up with the dynamic routing protocol? The one which is we leave determination of the path of any packet to the router. The router do math, the sum run calculation, and then from that calculation, we'll decide, this one is faster, I'm gonna take that direction. That's it. That's it. We can classify those ones into two branches. Something called exterior gateway protocol and the famous protocol of that BGP. And this is away from your study totally, because that's usually we use it between ISPs, IXPs, or in short, big companies, big corporates, which is big communication corporate even. So that's away from your study here totally. The one which we will focus on, we will focus on the interior one, the one between router to router. The exterior one can involve in what we call it AS to AS, autonomous system to autonomous system. What is autonomous system? I'll explain that to you in a minute. So we will focus on the interior gateway protocol. What exactly are those ones? That's the protocols which we use to route packets between router to router, one to one. We classify those ones based on the algorithm we use. So one of them, we call that the distance vector. That distance vector, the famous old technology, we call that RIB, which I believe some of you are familiar with that in the prerequisite unit, the basic unit. And we improved that to RIB version 2, but still not professional as it's old. It's old, where whatever you add to, still old. Then we have another protocol key called ERGP. That's a faster one, better, has high features. But that's use a protocol. And this one as well use specific type of algorithm. We call that Bellman-Ford. Okay, what is Bellman-Ford exactly? An algorithm which calculate the minimum distance between A and B. Really, yes, that's the whole idea. But we have different calculation. But at the end of the day, it calculates the minimum distance. Okay, let's just what exactly those ones. The Bellman-Ford algorithm, which cover the RIP and ARGP, based on concept, which is a router doesn't need to know about the whole network, but only you need to know information about your neighbors, direct connected routers. That's it. That's it. So if I am A and B and C and D, I need to care about A, need to care about B. B need to care about A and C, like this. Nothing like that. The link state, it use another algorithm, which is really famous algorithm. We call it Dectra algorithm. Do you know any application? Yes. If you use Google Map in your phone, that's actually based on Dectra algorithm. It calculates the distance between A and B for you every time you use it based on that algorithm, the Dectra algorithm. And the famous protocol which we use under that, the OSPF. What's exactly the comparison between Bellman-Ford and OSPF? Well, Bellman-Ford usually care about only direct link neighbors. Okay, and Dectra need to know about the whole network. Well, according to Cisco, they said from 0 to 15, that's 16 routers, but it doesn't matter for this unit. So the network, you need to know about all the network. If you have 5, 6 routers, every router need to know about the rest of the routers within that network. How we calculate usually in RIP, how the router calculate exactly. And that's one of the disadvantage with RIP. RIP, if I want to send the data from A to B, usually, let me just show you. If I want to send a data from A to B, okay, so I need to calculate how many routers I'm gonna take. If I take that direction, it will cost me 3 routers. If I take this direction, it will cost me 2 routers. So I'm gonna take 2 routers. That sound good, right? It's not. Why is that? Usually routers are not equal because sometimes you have two routers. For example, it take me, let's say, 20 milliseconds to reach my direction. However, I can pass by 6 routers and it come back within 6 milliseconds or 8 milliseconds. Really, yes. Believe it or not, for us here in Sydney to send the data to Perth, for example, it's better for us and faster to send it to the East Coast of the United States in California, then goes to Perth, rather than that to send it from here within the cables here inside Australia, because we have an old cabling. So it take, yes, it take more routers to pass through. However, it's faster. With RIP, they don't care about that because it's all technology. It's based on hubs only. I can go over here. It will take me 2. Over here, 5, take 2. That's it. That's it. But the 5 faster than 2, it doesn't matter. That's how it is. For the link state, we have some sort of metrics. What is metrics? Calculation. In here, we use method equation called 100 meg per interface. So what is in interface bandwidth? So you understand that we do have different type of cabling links. For example, we have serial links, which is usually kilobits. We have T1, T2, 1.5, 2.5 meg only. Then we go for the cat family from 5, 6, 7, and so on. Then we have something called gig cabling as well, which is up to 40 gig a second. So divided the 100 meg by the number I'm telling you. So from the cat 5, 6, 7 by the families of the cat category. So it's going to give you different numbers. We call that metrics or cost. So the value, when I divide that value 100 meg by the interface, it's going to give me a number. That number, we call it cost. The lower the cost, the better for the router. So if you have two interfaces, 1, 2, and 1, 5, the direction will take 2. If you have 4 and 7, the direction will take 4, and so on, like that, and so on. So to put a real comparison between the RIP and the OSPF, RIP, it's an old technology. It works with limited or smaller networks. And it has something which has the subnet mask as well. They don't have subnet mask, which is actually make it slower. And when exchanging the data, which I'm going to explain that to you later soon, they exchange the data every 30 seconds, the full table. So imagine if I'm a router and you guys are routers as well. And imagine if you have a database, smaller database as a router. And every 30 seconds, all of us, we send that to H1. Keep going like that. All the time, every 30 seconds. What does that create? It creates heavy bandwidth, which make the system slower. That's how it is. That's how it is. Then we have what we call it BGP. That's, as I told you, that's away from a study. To understand what is BGP is exactly the Border Gateway Protocol. It works between AS to AS. I put you something from mine. This is just only to explain to you the distance vector. As you can see here, router 4 need to know only about router 3 and router 5. That's it. That's it. And router 5 here need to know about router 6, router 7, and router 4. Doesn't know anything about those ones. Router 1 need to know about router 3 and router 2 only. And the rest of those ones, nothing. Only direct link I need to know about. That's the distance vector. So if I'm router number 1 and I want to send the data to router number 7, let's say, oh, okay, I need to know about that one, this one. So I send it a packet, and this one, responsibility to know about this one, and that one, responsibility to know about this one and that one, and this one need to know about 7 and 6, like that. Keep going like that. Is that professional? I don't think so. For the link state, as you can see that, router number 4 need to know about every router in the network. So need to know about R1, R2, R3, R5, R6, R7. And by the way, the other routers are similar. So router number 1 here has to have some entries inside the table, which I'm going to show you in few. Know about router 2, router 3, router 4, 5, 6, 7. So everybody knows about everybody. That's the link state approach. Up to here, you okay? Up to here, are you okay? You can ask me, Shloy, Zapala. Ask me if you want anything, just ask. I can explain to you again. No problem at all. Ah, a lot of information. Okay. That's how it is. Unfortunately, that's what it is. So, yeah, little by little, read and do some search. Try to, I believe, online because like the materials on doesn't have much. So just to go Google, if you can get a copy of the textbook PDF or the library, just to go to the library and try to have some reading in the book. Come back to me with any question you want to. For the AS, as you can see here, AS guys is like this. The ISP provider or the big corporate, big companies, whatever it is, they cannot configure they cannot configure router per router, one per one. Why is that? Because we have millions of routers here inside Australia, for example. Imagine a country like China, India, whatever it is. We have tens of millions, if not hundreds of millions. So what we do exactly, we cannot configure router per router, one by one. It doesn't matter. It didn't work like that. So what we do exactly, imagine this is like similar to the postcode. We group routers together, and when we configure them at once. If I with the same protocol. So I can configure them with the same protocol, with the same bandwidth, with the same delay, with the same metrics, with everything the same. That's it, that's it. And even if I want to change something, all. So not one by one. So we configure as a postcode, like let's say a postcode. So we call that like autonomous system. Um, what is the good with the autonomous system? Autonomous system, I can configure that AS with a protocol, another AS with another protocol, another AS with different protocol, with different protocol like this, and different bandwidth and different metrics and everything. However, for those AS to talk to each other, they need a special protocol called BGP, Border Gateway Protocol. And that's usually, as you can see here, we put it for you as static routing. What is the advantage of dynamic routing? You can put more, whatever you like. It's sure it's faster, easier, efficient. Load balancing. What you mean by load balancing? If I have topology and that router went down, the other one can take over, and especially with the big network. So if you have my packet goes that to that router, I think it's better if I draw you something. If I have this is the router and that's another router, that's another router. Here it is. Here. And let's say that's another router. Here it is. Here, here. Let's say that's A want to communicate with B, and I'm sending my packet. It take that direction. Assume that the calculation for the router here, after calculating the metrics, found out that low cost. So I'm gonna take router number two. However, router number two, something happened to it. What's going to happen? Router number one right away will decide to go over here or the other way around. Assume that right now it passed by router two, then find out that router, this one is down. So take it this direction. What about if I pass over here, then I found something wrong, pass it this direction, like this, automatically and dynamically from one to another. Scalable, I think the word scalability means like if you, I believe, you covered that in the prerequisite unit, but one more time will not hurt. Scalability means the network can expand or shrink without redesigning. So I can expand the system. For example, I have 1,500 students. Okay, let's give it a class. I have in my class 20 students. Then I can expand 22, 24, 25, 30, whatever it is, without any problem with the class. At the same time, I have 20, I can shrink to even 10 students without any problem. We call that scalability, ups and downs without redesigning. Something called route summarization, but let's go for the converge first. Converge, which I'm going to show you, when the router, the word converge, the state of the router to go from 0 until it finish the update of its routing table. In short, if I turn the router on and the routers on and they start to talk to each other, then they're going to start exchanging the data. Then every router or each router will build its own routing table. We call that converge, the time to converge. So how long it take? The converge here is much faster, better, a lot better, the converge. Route summarization, if you understand that, for the router does something which is actually a nice one. You guys study subnetting, maybe. We have covered some subnetting in the prerequisite unit. However, if I have network 192.168, let's say 10.0, 11.0, 12.0, 15.0, 20.0, like this. So when it passed by a router, what the router will do will summarize all of them. For example, here, this is 192.168, 0.0. That's CIDR 23, 2.0, 4.0, 8.0. That's slash 20 or CIDR 21, 22. So what the router will do exactly, will summarize those ones into one entry from 4, 5, 6, 10, 15 entries. Summarize those ones into one entry, 192.168, 0.0. Watch that. This is 2.0, 4.0, 8.0. However, here you can see that the CIDR 21, 22, 23, CIDR 12 subnet mask. So here, what we did exactly, we will slash it into 20. That's another story for subnetting. We call that route summarization, one of the advantage in dynamic routing, which is excellent one. The dynamic routing provide as well something called high availability and load balancing, which means that if I have, for example, 3, 4 routers here, and instead of one router carry everything, some goes here, some goes there, some like this. That's load balancing. High availability, something like redundant. Redundant means like you have 2, 3 router do the same job. If one of them dead, the other 2 take over. Another one did like this. We covered that in the prerequisite unit. If you don't remember, is okay. How the routing exactly we do? Every router has something called the routing table. If you type show IP route in any router after you configure one of those protocols, RIP, OSPF, ERGP, you will find something similar to that. Similar, not 100%, but that's similar. For the RIP, for example, this is if that's router number 1, the C here, it mentioned that directly connected. The L, local. And the R, that's RIP. So what's here exactly? What's here? What we are seeing here? It tell me that 192.168.3.0 CIDR 24 with the matrix via 192.168.2.2. Okay, so if you want to reach via, I can reach that 3.0 via 2.2. Okay, and this is the timestamp. Where to go? I can take it to serial 00. The same thing, 4, I can take it to serial 00. Same one, but different metrics. As you can see that's serial 00 as well. From here, we can see that exactly that's what routing option I have in my table and how being calculated. I put you that from my own, just only to the concept usually inside the router. What usually happen here? Let me just show you some of those. Let me just show you this one. I think that's much better. Let's start from scratch. Those are 3 routers. You have network 1, network 2, network 3, network 4. That's updating. So what those router will do, inside the router usually, every router at the beginning, what every router will do will start include its own only interfaces. For example, router number 1 will focus only on network 1 and network 2. Put them here. What's the interface? If you want to go to network 1, go to the fast 00. If you want to go to network 2, send it to 000, right? Okay, that's direct connected network only, the links. So router number 1 will do that. Router number 2 will care only about 2 and 3. Router number 3 will care about 3 and 4. That's it. Nothing else. So after everybody care about itself only and got the data about each link. So router number 1 knows only about 1 and 2. Router number 2 knows about 2 and 3. Router number 3 knows about 3 and 4. That's it. So what they do, they start exchanging the one I told you about it in RIB every 30 seconds. So sending the data. Router number 1 will send its own table to router number 2. Router number 2 will do the same. Router number 2 will send its own update from router number 1 to router number 3 with its own date table as well after updating. So router number 1 will tell router number 2, here it is. If you want to go to router number to 10.1, send me your packet. And okay, how many hops I will need? One only. So just only to pass it to me. If you pass it to me here, it's only one router. Can you see that? One hop. So pass it to me, it's gonna be 1. So in short, if packet from here want to go here, that router knows exactly that I have to pass by router 2 and router 3, which is 2 hops. So you will find that inside the routing table, that's the network you want to go, which interface you want to take, and how many routers. That's it. That's usually after the updates. After everybody update everybody, that's what usually in the link state, the one which is the big ones. For the RIB, they don't. RIB just only care about me, and direct link only. Direct link only, direct link only. I got you something about here. This is the distance vector. That's it. You have a router and you have another router. That router usually, as you can see that, sending and receiving updates. Okay. I'm going to send it to my next network only. So router number one right now knows that, if you want to go to 172.16.1.0, send your packet to me here. Okay, how far it will take? It will take you only one router. That's it. That's it. Here it is, similar to the other option. So if I want to go to 1723, which is this one, it will cost me one router. If you want to go to 16, it give me one router. That's it. That's it. In the link state, they update each other one to one to one to one until the whole network do math and calculation and find which one is the best calculation. So I want to go from router 1 to router 2, it costs me 3. But there's another way I can go, but cost me 2. No, take the other way. That's what it usually does with link state. That's another approach. Just remember that place inside the routing table. Usually you will find something about what is the network you want, which network you want to hit, your goal, your target or destination. Then you have something about metrics, which is in RIB, how many routers. As you can see, that's a very easy one. How many routers? In the link state, it has something cost, math, which you will see that. That's the subnet mask, next hop, and the interface. We have different approach as well. How we actually update the tables, or the table itself, usually how it being updated when it's updated automatically, for example. I can do that manually if I want to, but usually automated. When the router, they start talking to each other, they update each other. This is an example, the one I just showed you at the beginning. And this is, as you can see, that's the dynamic routing. The static routing, we type IP route, which network you want, and the destination, which is the next hub. Call that the next hub. In the dynamic routing, we type router rib. Usually we follow that with another statement called version 2. But anyway, then we mention the network. What is that? The direct link network. Only. So for example, we have here 192.168.1.0, 2.0, 4.0, 5.0, 3.0, right? Okay, we have 5 networks. That router, when I configure it with what? That network and that network. Only. That's it. That's it. When I come to that router, I configure it with what? That one, that one, that one. 3 networks, which is 2, 4, and 3. 2, 3, 4. 192.168, 2.0, 3.0, 4.0. How the router they talk to each other, you may notice that 2.0 here is coming between router 2 and router 1. That will make the neighbors, will make the router 2 of them talk. Then we come to the router number 3. Router number 3 care about only 5 and 4. 4, as you can, like you can tell that coming between 2 and 3, they will talk to each other and they will making neighbors. So they can talk to each other. That's it. That's it. Nothing more than that. How the packet will be delivered? Are you okay up to here? Just before we move. Are we okay up to here? How the, all right, thank you. How we deliver the packet from one area to another area, it's easy, by the way, don't get me wrong, that's a very easy one. You have something called direct delivery and indirect. What the difference between? Direct delivery, if you deliver a data within the same network, within the same subnet. Indirect delivery, it's not. Another way, direct delivery when you do not cross a layer 3 device. Indirect delivery when you cross a layer 3 device, which is a router, for example, or layer 3 switch if you are familiar with that. So how that works exactly? Here. So I want to send the data from A to B. That's a switch. This is one is a switch. So if my packet goes to the switch from the switch to another device, that's normal, no problem. That's direct delivery. From the router to A or from the router to B, still within the network. And if you want to get that within when I have something like that, that's router number one, for example, then I have a switch or multi switches, whatever you want to put it on. That's S1, S2. Then you have PCs here or servers or whatever it is, whatever you want. So the data, when PCs or servers, they start talking to each other within that, we call that direct. Why is that? Because all of them, as you can see here, is a one subnet or one network. But if I have another network here, this is router number 2, and I want to send the data to another network. So it's gonna pass from my router to another router. We call that indirect. So if my packet pass layer 3 device like this one, for example, that's A, and that I want to pass by B, you have to cross that router, then another router, then pass by that. So if you pass just one router, if you pass that to another network, which means that that's indirect delivery. So within the network itself here, direct, if you pass from here to here, that's indirect delivery. Inside the network, you may find the router switches, layer 3 switches, which is work as well inside one network. If you have a university, for example, the university has a big campus or multi-campus, and inside that campus, usually you have routers, you have switches within the same campus. The router usually has something called forwarding, routing and forwarding. What the difference? Routing is like when you have the router like that and you have the table inside. The router usually, I have a packet here coming from the network 10.0. That network, it's want to go to network 20.0, 192 or 172, whatever you like. The router will look inside the table right away and start to look. This is usually take between 2 milliseconds, 4 milliseconds, depends on the router. Something very fast. Don't get me wrong. Okay, so the router usually has multi interfaces like that. Serial 00, 001, 010, 0110, like that. So if you talking about serial, like which interface I'm gonna take, which whatever it has to be. So I decided that this is my here, send it to serial 000, here, and here. Been decided, that's routing. It been decided. Now, forwarding. Forwarding means I need to take that packet from here to that interface. We call that forwarding. And usually, forwarding involves something called queuing. But anyway, that's the concept of forwarding. Forwarding means take it from either the entry interface or from queuing the interface, from queuing memory into the next interface. How we forward techniques exactly, we give you some options here. We have the next hop, um, the specific entries. If I have specific entries in my system, if I want to send it to a specific host, and the default entry, which is a good one. I'm going to focus on that default entry. What is next hop exactly? Here it is. That's router number A, for example, host A, and that's I want to send it to host B. That's A and B. Okay, so what's inside the host A routing? The table. Oh, I want to cross router number 1, then cross now router number 2, then I reach the host B, which is this one. So up to here in that area, host A in its own table has entries about router number 1. I need to pass that. Router number 2, I need to pass that. Then I need to go to B. Okay. So what about if the routing table was based on the next hub? What's inside? I want to go to the host B. So what to do exactly? Oh, I don't care. Just only pass it to the next hub, which is router number 1. That's it. That's it. So the difference between that's the routing based on route, and this is based on next hub. Next hub, I don't have to keep any data within my table, the routing table, except that the next router, or what we call it next hub. So if I have to pass here by 6, 7 routers, I have to keep a routing entries for those 6 or 7. I don't need that. But if I go with the next hub, no, just only. I want to go from host A to host B. What I care about, router number 1. And router number 1 care about router number 2. And router number 2 will pass it to the host. That's it. That's it. That's network specific approach. And as you can see here, the network specific, you have inside the network, maybe you have, this is the routing table for the S device. That S device, whatever the device, PC, that PC belong to a network. So what that PC has inside its own table. Oh, if I want to go to A, send it to router 1. If I want to go to B, send it as well to router number 1. If I want to communicate with C, send it to router number 1. So it's all about what? If you want to go to anything, anywhere within the network number 2, the second network, send everything to router number 1. That's it. That's it. However, it looks like the next routing or the next hub, but over here, because it's a smaller version of the next hub, a network specific. So you actually target a network, not a specific host. Here you can actually target a specific host specific, router number, host A, and host B, and host C. What's inside host A routing table? Easy. I want to go to host B. So if I reach from here, can I take network tree. So if I go to network tree right away, I have to pass by router 3. But if I want to go through network 2, I need to go router 1, which makes sense. What about if I want to go to router or network 3 again, but not from here? Oh, I can go to router 3 as well. Really? Yes. So I can go to host B by itself through the router 3. I can go to the whole network through router number 3. Host specific, this one. So I can put an entry, a single entry, not us, for example, but can be the forward, can be specific to a specific host. It doesn't have to be a whole network. This is a good one, which in my opinion, that's the one which is you need to cover when you configure networks. We call that the default routing. What is default routing? Usually, you have entries here in 1, 2, 3. Okay, what about if a packet arrive at the router here and that router, for example, I want to send a packet. Usually when router send it to another one, the router will do what? Will search inside the table. I need that entry. If it exists, forward. If it's not exist, usually drop it. So to avoid that, because like you actually passing by a router and in the router has a table. That table has 192.168, 1 whatever, 60 whatever, 172, whatever it is. So you send in packet pass by me. I don't have any entry at all for it. So what I'm going to do, usually drop the packet. To avoid that drop in packet, what we usually do, we configure what we call it default routing. And we tell the router, if you can find anything at all, whatever it is, send it to what? Anything you want. You can configure it with any number. But in most of our works, we usually send it to 0000, subnet mask 0000, which is usually we represent that to the higher router, which connect to the internet, the ISP, the last one. So something like that. I got you this one to represent the OSPF. I have that's router 1, router 2, router 3, all those ones here. Usually you have something called a gateway, and then from the gateway, we configure something as well from my router to the ISP. From the router here to the ISP, we configure that static routing, IP route 0000 here, which means that send everything, every default route, we call that default route, send everything to the ISP. Similar concept apply to here. If you want to forward something, I want to forward something like this is N2. I have to send it to R1. Okay, the default R2. So what is default exactly? Something which is not here. So I want to send a data not in N1, not in N2. So where to send it? To the R2, which is the default, usually router before the ISP. One more thing to learn. This one we covered that in the prerequisite unit. What is that exactly? That's the maybe yeah here that's the one. So we covered the classful, the classless, if IP addresses, if anybody still remember. The classful, which is class A, class B, class C, from 0 to 126, and the 126. They call it 127, but in reality, end of 126. Then 127 is reserved for looping and troubleshooting. But anyway, from 0 until 127, that's A. From 128 until the end of 191, that's class B. Any IP start with. and class C from 192 until 224 and the end of 2024. After that, been reserved D and E for development and multicasting. So what is the idea here? Oh, class A has subnet mask 8, which is 255.255.255.0.0.0. Class B, 255.255.0.0. Class C, 255.255.255.0. Static. We cannot do anything with that. Any IP from 0 until 127, it has to take that subnet mask. Any IP from 128 until 190, end of 191, it has to take 255.255.0.0 and so on. So in reality, what exactly need to know when I try to forward classes? Forward classes usually involve, that's one of the things which I put it for you as well. That's class A, as you can see here, 8 bits only for the network, and here 16 bits, over here 24, and the other way around for the subnet mask, which is the host part. So if I want to route using classful, I need 3 things only. We'll call that 3 columns. I need to know about the destination, the next hop, and the interface. One, destination, next hop, and the interface. We have something called classless, which we covered that as well in the prerequisite unit, which means that I need to add the slash or the cider. Why is that? I can use the same IP with different subnet mask, with different cider. That's it. That's it. Easy as that. This is an example of the classful routing. As you can see that the router over here, I have 170. Oh, 170. That's a class what? Okay, so what is the number? So that's 145. Start with 145. What's that class? Start with 111. What is class is that? 192. So you can see that over here, that's class A. Why is that? Because we said that from 0 until the end of 127. So this one will be class A. Okay, what about 145 and 170? Oh, that's class B, both of them. What about 192? Class C. That's it. That's it. Easy as that. Easy as that. Classless routing, as you can see, that's the idea of the good thing with the classless routing, which is you can use the same IP address. At first, there is no classes, which means that you cannot tell me that this is subnet mask 255.255. You can't. So what determine exactly the subnet mask? The CIDR or the slash here. The slash 25, that's the CIDR, the subnet mask. So 24, 22, 26. That's what it tell me exactly. That's the subnet mask. So there's no classes. There is no classes. So for example, the 180, the next hop, for example, that's M2 slash 26 slash 25, 24, 22, and so on. You may have noticed that 180, 170, I'm sorry, 180, that's 70, 65, both here and here, the 3 octs, the 3 beginning octs, similar. However, when it comes to the last oct, this one start from 128, this start from 192. And that's the beauty of using the classless. And as you can see, the last one, the default send it to where? Default, send it to where? 180, 70, 65 to 1, which is outside here. That's the default, which is M2. Another piece, which is We covered that mostly. What is how we represent the metrics? How we represent metrics. In the table, usually you have the destination, the interface, and how the cost, how many. The lower the cost, the better for us. So if I got option to send a data through 1 or 2, I'm gonna pick, the router will pick 1. From 2 or 5, the router will pick 2, and so on and so on. But usually that's how how it works. What about the other options? And we call that distribution or distributed one. Um, each node communicate only with directly attached one. Okay, the distance vector, each node notify neighbors only when it least cost path. What is that? What you try to say here? You remember when I told you about that in RIP? When a router, when you have routers like that, when I have some routers like this, let's say, assume that these are communicated routers. In RIP, every 30 seconds, all those routers, they have to send their packet like this, update like that, all the time, which create a lot of hassling and consuming bandwidth and slower the system. With the link state, which is OSPF, we will not cover that much today, but a small hint about that. With the OSPF, when they try to improve that, or any link state protocol you want to work with, they said, no. Those devices will talk to each other only at the beginning of building their network. Only. And they will send their data, like my table. This is my table. That's my table. That's my table. We're done. You built your own table. I built my own database. Everybody built. Everybody happy with that? Yes. We agree on that? Yes. I'll see you when something happens. What do you mean by that? I will exchange my table with you again in case if something happened. An interface went down, something happened with whatever, the matrix has changed, anything has changed. Whatever something, if something has changed in the network or the links, I'll get back to you. But everything, if everything stayed quiet, everything is cool, everything is nice, whatever it is, we between both of us only something called hello packets. Yes, we have something called acknowledgement, whatever packets away from study here for now, but the main thing you focus on, I will get back to you if something happened. In case if something happened, I'll get back to you. What that mean? The bandwidth is saved. There is no much traffic on the links. Only the traffic being consumed when there is a data, actual real data, services. Is that better? A lot better. A lot really better. One of those protocols, which is the link state protocol, the OSPF. OSPF, by the way, work with subnet mask and something called wild card. So I can actually specify the network in maybe not very quick. So in RIP, when you here, let me just go back here. I can show you without when we configure RIP, for example, when I try to configure the RIP here, you have noticed that we put the network 192.168.1.0 without any subnet mask. What does that mean for the router? The router has to go through a lot of calculation for every possible subnet mask from 0, which is until 20 until 32. So from 0 to 32 has to be all the calculation. What is that? A lot of hassling over the CPU and the memory, which is more delays. With the OSPF, we don't have that. We can specify as well. We can specify here what subnet mask I'm using. What is that? Faster search or faster data lookup. One last thing before I'll let you go, just to go over those one place. Come back to me with any question. I know I understand we teach how that works and everything, and I can show you a demo for that one as well, how it work in reality. I have something to that. You can see how it works, but away from study here for now. Go over the materials, review maybe the lecture one more time, Google, AI, whatever you like. Just do some reading, and whatever you stuck with, come back to me. I'll be more than happy to explain that to you as well. Questions? Questions? No questions. Last call. Last call. No, no, no question. All right. Thank you, Head. Thank you, Taker. All right, ladies and gentlemen, if you don't have any question, if you don't have anything, feel free, and I'll see you next week. Have a good one. If maybe next week is a public holiday, we will have some arrangement. Have a good one for now, and I'll see you the next lecture. Have a good one.